Today we are looking at unconstrained optimization. Our learning objectives will be to work out first order conditions, work out the eigenvalues of a Hessian matrix, compute first order conditions in the Hessian matrix, and then use the eigenvalues of the Hessian matrix to classify optima. Constrained optimization allows us to find the maximum or minimum of a function where there is no constraints, hence why it's unconstrained. Step number one in the process of finding the maximum or the minimum is to first find the stationary points using first order conditions. Step two would then be to compute the Hessian at these points. And then step three is to work out the eigenvalues and using them to classify the optima. So if we look at step number one closer, step number one is about first order conditions. So at any local optimum, the gradient must be equal to 0. This means that for a multivariable function, for example, a function which has variables x and y, we need the partial derivative of the function with respect to x to be equal to 0, and the partial derivative with respect to y of the function also has to be equal to 0. And then we would solve these two first order conditions to find the optima. Step 2 is to then calculate the Hessian at our stationary point, so whatever our solution is to these two equations. And the Hessian for a function with two variables is listed as this. So the Hessian is just all the second derivatives of a multivariable function. So in this first entry, we have the function partially differentiated twice with respect to x. Over here, we have the function partially differentiated with respect to x and y. That's the same over here. And then over here, we've got the function partially differentiated with respect to y twice. And what the Hessian tells us is the curvature of the function at that point. So if we work out the eigenvalues of the Hessian, they tell us if our point is a minimum, maximum, or a saddle point, or even if the test is inconclusive. That's because the eigenvalues tell us if the Hessian is a negative definite or a positive definite. So if we look at the eigenvalues, if both of the eigenvalues are greater than 0, so in other words they're positive, then we have a local minimum. If both of the eigenvalues are negative or less than 0, then we have a local maximum. If there's mixed signs between the two eigenvalues that we get, then we have a saddle point, and if any of the eigenvalues are 0, then we have an inconclusive test. So if we look at some questions, question number 1, we have a function which has variables x and y, and that is equal to x squared plus y squared minus 4x minus 6y plus 13. So what we first need to do is find the first order conditions. So I'm going to partially differentiate with respect to x. That gives me 2x minus 4. Partially differentiating with respect to y gives me 2y minus 6. And our first order conditions are always equal to 0. So we get 2x minus 4 is equal to 0, and 2y minus 6 is equal to 0. So this means x must be 2 and y must be 3. Cool. What we will now do is work out the Hessian. So if we differentiate this with respect to x again, we get 2. If we differentiate this with respect to y, we get 0. If we're differentiating this with respect to x, we get 0. If we differentiate this with respect to y, we just get 2. So this is our Hessian From this, we can clearly see that the Hessian is a positive definite. And because this Hessian is also a diagonal matrix always has its eigenvalues in that leading diagonal. So we know that the eigenvalues will just be 2. If we did want to check that, we can use the characteristic equation. So we get lambda squared minus the trace of h lambda plus the determinant of the matrix H. So we get lambda squared minus 4 lambda plus 4 is equal to 0. So we get lambda is equal to 2. So we get lambda minus 2 and then lambda minus 2. So lambda is equal to 2 and 2. Cool. Because both eigenvalues are greater than 0, they're both positive, we have a local minimum. Cool. Looking at question number 2, which is a bit harder, something that we might actually see in an exam. An agent derives utility from consuming 2 goods in quantities x, y, and investing time, where that time variable is obviously going to be greater than 0, and the time variable is z, in a leisure activity. Her utility function is as above, so this is her utility function, where aj is greater than 0 for j is equal to 1, 2, and 3. So all of these are greater than 0, and they represent the rates at which overconsumption and overexertion generates a negative health effect. Cool. If we first, like always, find the first order conditions, we will differentiate with respect to x first, and so we get 1 over x plus minus a1 over 2 times 2x. Partially differentiating with respect to y gives us 1 over 3y plus brackets a over 2 4 times 4y cubed. And finally, partially differentiating with respect to z gives us 1 over 2z plus brackets minus a over 2 divided, a over 3 divided by 2x. Cool. Over here, this has both variables x and z, which I did not see beforehand. So over here we'd get minus a over 3 over 2 and then times z. Cool. Hopefully you are happy with that. What we will now do is equate, should be a minus sign over here. We will equate all of these to 0. And so we get 1 over x plus 1 over x minus a1 x minus a over 3 over 2z is equal to 0. Over here we get 1 over 3y minus a2y cubed is equal to 0. And then finally, over here we get 1 over 2z minus a over 3 2x is equal to 0. If we first go about solving this equation, we get 1 over 3y is equal to a2y cubed. So 1 is equal to 3 a2y to the power 4. So y is equal to the fourth root of 1 over 3a2. If we now have a look at this equation, we can rearrange it. So we get a 3 over 2 x is equal to 1 over 2z. And looking at this equation, we can write 1 over x minus a1x is equal to a3 over 2z. I am now going to make z the subject for this equation. So we get 2 over a3, x is equal to 2z. So z is equal to 1 over a3x. If I substitute that over here, we get 1 over x minus a1x is equal to a3 over 2 times 1 over a3x. So we get 1 over x minus a1x is equal to 1 over 2x. This we can write as 2 over 2x minus 1 over 2x is equal to a1x. And so we get 1 over 2x is equal to a1x. So we get 1 over 2a1 square rooted is equal to x. That means z is equal to 1 over a3 times 1 over root 2a1. So z is equal to root 2a1 all over a3. Cool, so if I write our solutions more clearly, we get this. And now to determine the nature of this optimum, we'll have to compute the Hessian. So if we look at this, we can write this as x to the minus 1. If we differentiate this with respect to x, we get minus x minus 2 minus a1. Differentiating it with respect to y would just give us 0, and differentiating it with respect to z gives us minus a over 3, 2. Differentiating this with respect to x gives us 0. Differentiating it with respect to y gives us minus 1/3 y to the minus 2 minus 3 a2y squared. Differentiating it with respect to z gives us 0. Differentiating this now with respect to x gives us minus a3 over 2, 0, and then minus 1 over 2 z to the power of minus 2. Cool. So here's our Hessian. If we now sub in our stationary point, we get minus 1 over 2a1 minus a1, 0, minus a3 over 2, 0, minus 1 over 3, brackets, root 3a2 minus 3a2, 1 over root 3a2, and then 0. And then we get minus a3 over 2, 0, minus a half a squared 3 all over 2a1. If we now simplify some of this, we get minus 1 plus 2 a squared 1 all over 2a, 1, 0, minus a3 over 2, 0. So here we get minus 4 over 3 root 3a2, n minus a3, 2, 0, a squared 3 all over 4a1. That's what we get over there. Cool. If we now work out the eigenvalues of h, so that h minus lambda I is equal to 0, we get the same matrix, but now with minus lambda in the diagonals. I will now use the second row to work out. So if we work out the determinant using the second row, we get this. What we can do is times everything by a minus. So if I take out the minus of this bracket and then times everything by this said minus, everything will become positive, so we get positive lambda there. We get this. So now we get 4 over 3 root 3a2 plus lambda times 1 plus 2a squared 1 2a1 plus lambda multiplied by a2 3 4a1 plus lambda subtracted by a squared 3 all over 4. That's equal to 0. So what we can instantly say is that from here, first eigenvalue is equal to minus 4 over 3 root 3a2. If we now expand the bracket, we get a squared 3 plus 2 a squared 1 a squared 3 all over 8a squared 1 plus 1 plus 2a squared 1 all over 2a1 plus a squared 3 all over 4a1 plus lambda plus lambda squared, and then minus a squared 3 all over 4. Cool. If we collect these two together, we get everything over 8a squared 1, which means that I times this by 2a squared 1. So our top becomes 2a squared 1, a squared 3. So it turns out that these two cancel, so we just get a squared 3 on top. Collecting these two up isn't really going to help us, but we get 4a1 at the bottom, and then 2 plus 4a squared 1 plus a squared 3 lambda plus lambda squared is equal to 0. So if I now write our characteristic equation for finding our eigenvalues of a 2 by 2 matrix, it was lambda squared minus the trace of the matrix, and then lambda plus the determinant of that matrix. So over here we get the determinant of that matrix, which we can see is positive. Then we can see that the trace of the matrix is also, as a whole, including this minus sign, is positive. What that means is that the trace would have to be negative. Hopefully that made sense. So we've got a positive determinant and a negative trace. What we should also remember is that the trace is the sum of eigenvalues, and our determinant is the product of eigenvalues. So we've got a sum of two numbers, and it is negative, and then we've got the product of those two numbers, and it is positive. That means both of those numbers have to be negative. So we can say that these two eigenvalues have to be negative. So if lambda 2 plus lambda 3 is less than 0, and lambda 2 times lambda 3 is greater than 0, then lambda 2 and lambda 3 both have to be less than 0. So we both get negatives for this, and then over here we can see that our first eigenvalue is negative, so we can conclude that the nature of this optima is a maximum. Cool. Hopefully that made sense. If we now take a short break from all of that algebra and look at a much easier question, we've got a function which has variables x and y, which is minus x squared minus xy minus y squared plus 4x plus 2y. If we work out the first order conditions, so our first partially differentiate with respect to x, we get minus 2x minus y plus 4. And then partially differentiating with respect to y, we get minus x minus 2y plus 2. And both of these are equal to 0. If we now solve this, we can rewrite this first equation as 2x plus y is equal to 4, and this second equation as x plus 2y is equal to 2. So we get x is equal to 2 and y is equal to 0. If we now work out the Hessian, differentiating this with respect to x gives us minus 2, differentiating it with respect to y gives us minus 1, differentiating this with respect to x gives us minus 1, differentiating it with respect to y gives us minus 2. So this is our Hessian. If we now work out the eigenvalues, we get lambda squared minus the trace of the matrix plus the determinant is equal to 0. And over here I'll just write the full thing, or the full method. So this formula gives us our characteristic equation. So we get the matrix A minus lambda, the identity matrix. So we get minus 2 minus lambda, minus 1, and then minus 2 minus lambda. If we now work out the determinant of this matrix, we do AB minus AD minus BC, which is equal to 0, where A is this entry, B is this entry, and blah blah blah. So we get minus 2 minus lambda multiplied by minus 2 minus lambda, and then minus 1 times minus 1, which is 1. So we get minus 1 is equal to 0. If we expand this bracket out, we get 4 plus 4 lambda plus lambda squared minus 1 is equal to 0. So lambda squared plus 4 lambda plus 3 is equal to 0 is our characteristic equation, and we can check that over here. So if we look at this, we get lambda squared minus the trace of the matrix, which is just these two summed together. So minus 2 add minus 2 is minus 4. So when we plonk minus 4 into here, we just get plus 4 because of this minus sign. So plus 4 lambda. And then plus the determinant of this matrix is just minus 2 times minus 2, which is 4, minus minus 1 times minus 1, which is 1, which is just 3, is equal to 0. So we get lambda is equal to minus 1, and then lambda is equal to minus 3. So both eigenvalues are negative, so it is a local maximum. Cool. Okay, if we look at question 4, we have an agent who manages a portfolio of n assets. The utility over returns is given by this equation above, where pho is greater than 0, which is a risk aversion parameter, and Cij is a symmetric positive definite matrix capturing the covariance of returns between assets I and j. For the remainder of this question, take n is equal to 3, and this is our matrix C. So what we're going to do first is just look at this little sum problem here. So what this equation is saying is we're looking at the utility over some returns. So this would be the return of the first asset, then the second and the third all added together. And then over here, we've got two sums of xi, then a matrix, and then xj. So if we take a closer look at this, this can be written as our matrix C multiplied by x, and we're just going to take the ith entry, I guess, between C and this vector x. So what that then leaves behind is us doing the sum of Cij and an xj. For example, if we had a matrix 2, 4, 3, 2 multiplied by some vector, which we'll call 2 and then 4. So here we've basically have n as 2. If I was working out Cx1, we would have 2, j is equal to 1, and then C1, j, xj. So this would just be C11 x1 plus C12 x2. So this gives us 2 times 2, and then plus 4 times 4. So we get 4 plus 16, which is 20. So hopefully you can notice this is just the definition of a matrix times a vector. So a matrix vector multiplication. Now what we will do is get our matrix C and then our vector x, and we will multiply it by the transpose of x. So what this gives us is n, and then I is equal to 1, xi multiplied by cx and I. So once again, just using this same example, we are now saying that we're getting the sum of 2, I is equal to 1, x is equal to, and then xi, and then cx brackets I, and that is equal to x transpose c and then x. So if we use this on this matrix, okay, if we now use this on this matrix, we get x1 and then cx1 plus x2 cx2. So x1 is just 2 from over here, and that is going to be times by our answer from over here, which is 20. And x2 is 4, and we're multiplying that by cx2, and we know that that means we're just replacing this with a 2, So we'll get a 2 over here. And from before, we know that this is just the formula for row times column. So we're essentially doing this row times this column, which is 14. So 4 times 14, which will be 96. So what we've done is these two, this matrix and this vector, multiplied by that same vector, which is now being transposed. Now, of course, you might be wondering why I've written this. That is because we can write this as this sum. So we get this sum multiplied by this sum, which we can put together as xi, cij, and xj. So what we have just shown is that this sum is just the same as doing the vector x transpose multiplied by c multiplied by the vector, which is helpful because we now don't need to sort of look at that sum anymore, because we know that sum is just this. What we are now going to do is work out the first order conditions equation. So we have utility of assets x1, x2, and x3 is equal to the sum I is equal to 3, I is equal to 1, 3 ln xi minus pho over 2 x transposed c and an x. So over here we get ln x1 plus ln x2 plus ln x3 minus pho over 2 x1, x2, x3 multiplied by 210, 121, 012, and x1, x2, x3. So we get this, and so we get this as our fully expanded version. So now we can work out the first order conditions. So 1 over x1 minus pho over 2 for x1 plus x2 partially differentiating with respect to x2 gives us 1 over x2 minus pho over 2 brackets 2x2 plus x1 plus 4x2 plus x3 plus x3. And partially differentiating with respect to x3 gives us 1 over x3 minus pho over 2 brackets x2 plus x2 plus 4x3. Cool. I've just realised that this should in fact be x1, x2, which does this. We would get x1 plus x2, sorry, plus x2. Other than that, I believe everything is correct. So over here we get 1 over x1 is equal to pho brackets 2x1 plus x2. Over here we had 1 over x2 is equal to pho 3x2, because this should be a 2 because there's 2 sets of them now, plus x1 plus x3. And over here we get 1 over x3 minus is equal to pho 2x3 plus x2. Okay, from here, hopefully we can see that this equation and this equation are pretty much the same. So what I'm going to do is let x1 equal to x3, which I will let to be equal to some constant a. That is because we then get 1 over a is equal to pho 2a plus x2. And I'm just going to call x2 b, just so that it's quicker for me to write. And if I were to change this, we would get the exact same thing. 1 over a is equal to pho 2a plus b. So I've sort of eliminated, in a sense, this equation. And if I rewrite this equation, we get 1 over b is equal to pho 3b plus a plus a, which we can just write as plus 2a. Cool. If we now look at these two equations, we have 2 pho a squared plus AB over here, and then 1 is equal to 3 for B squared plus 2AB. I will make B the subject over here, and then substitute it into here. What I will now do is equate these two equations. This equation can be written as 1 is equal to 2 pho A squared plus pho AB, and over here we get 1 is equal to 3 pho B squared plus 2 pho AB. I'll then equate these two equations together, which means that I will be able to divide by pho, which I'll just do now. So we get 2a squared plus ab is equal to 3b squared plus 2ab. So over here we get 2a squared minus 3b squared minus ab is equal to 0. What I'm now going to do is divide by b squared. So we get 2a squared over b squared minus a over b minus 3 is equal to 0. Very difficult to spot, but hopefully you can see that this is a disguised quadratic. A bit more obvious if I make r is equal to a over b. We get 2r squared minus r minus 3 is equal to 0. And so we get r is equal to 3 over 2, r is equal to minus 1. So a over b is equal to 3 over 2. And then a over b is equal to minus 1. So a is equal to 3 over 2b, or a is equal to minus b. If we just put that into one of the equations above, we will do 1 over b is equal to pho 3b plus 2a. We have 1 over b is equal to pho 3b plus 3b. So 1 over pho is equal to 6b squared. So b is equal to 1 over 6 square rooted. What I've just realised is if I scroll all the way up here, this is unfortunately incorrect, because when I partially differentiate all of this with respect to x2, I get 2x1, 4x2 plus x3 plus x3. I unfortunately don't get this one, so this just turns out to be 2, and so this turns out to be 2, and so this will be 2. This turns out to be 2, this turns out to be 2, this turns out to be 2. And unfortunately, our solutions don't end up being that nice. Unfortunately, I am a bit sick and tired of this question, and to be honest, I really don't want to be using 1 plus root 17 over 4. So I'm going to put a halt on that and just let the optimum values be a mystery. What I will instead look at doing is looking at the Hessian. So this is our Hessian. If we work out the eigenvalues of this matrix, we'll have to do det h minus lambda I is equal to 0. So we get minus lambda, minus lambda, minus lambda. So working out the determinant using the first row gives us that, and then plus pho minus x squared minus 2 pho minus 0, 0 minus pho is equal to 0. If we times everything here by the minus, we just get x squared plus 2p plus lambda, and then if we work out the determinant, we just get x squared 2 plus 2 pho plus lambda, x squared 3 plus 2 pho plus lambda minus pho squared, and then plus pho times pho is just minus pho times minus pho is just pho squared, and then it's just 0. So we just get pho cubed is equal to 0. If we now expand this out, we get x squared 2, x squared 3. For this particular question, we are, instead of using eigenvalues, we're going to use the principal minors method. So what that means is we look at the determinants of the top left submatrix and we increase in size every time. So here we'll start with h1, which will just be this first entry, which is minus x squared 1 plus 2 phi plus lambda, and plus 2 phi, which we can see will be less than 0, because that must be positive, because anything squared is going to be positive, and then 2 phi is positive because phi is greater than 1. So this is going to be a rule less than 0, because this positive is being times by a negative 1. If we then look at h2, we can see a fairly similar pattern. We get minus x squared plus 2 phi multiplied by x squared minus 2 phi, x squared plus 2 phi. So that's me doing these two times together. And I've taken out the minus from this, which is over here. And if I take out the minus from here, we just get plus. And then we get minus phi squared. So as you can see, this will be greater than 0. If you are unsure, we could always expand the bracket. And so we get x to the power 4 plus 4 phi x squared plus 4 phi squared minus phi squared. And then this just becomes 3 squared. And of course, all of this will be greater than 0. If we finally work out h3, we get this diagonal times together, which will be minus x squared 1 plus 2 phi, x squared 2 plus 2 phi, and that now becomes positive, and then times x squared 3 plus 2 phi. Because I've taken out the minus from here, this positive now becomes negative, and then we get this diagonal, which is just 0, and then this diagonal, which is in 0 again, and then we subtract this from this diagonal, which is just 0, this diagonal, which will be phi squared brackets x squared 1 plus 2 phi with that minus outside, and then this diagonal, which is minus phi squared x squared 3 plus 2 phi. This we can see is going to be negative because I can take out a minus sign from all of this. So this is negative. So whenever we have this pattern of negative, then a positive, then another negative, it means that we have a local maximum. If it was that all the principles were greater than 0, it would mean that we had a local minimum. Cool. That will be the end of this lesson. Hopefully you find that useful. Next time we will look at constrained optimization, so I'll catch you in that video. Bye bye.